Welcome to ERC TipsKnowLogy. In this video, we will be talking about the field effect transistor, or FET. If you will remember, or if you have watched my or our old videos about the bipolar junction transistors, or BJT, the FET is the second major type of transistor. So let's start. Now, in the FET, we have what we call as the FET family, and the FET family consists of JFET here, and we have another one which is MOSFET or MOSFET. For JFET, we have depletion, and under depletion, we have P channel and N channel, or simply we say P channel JFET and N channel JFET. On the other hand, for the MOSFET, we have what we call as the P-channel depletion MOSFET and the N-channel depletion MOSFET. We also have the P-channel enhancement MOSFET or P-channel E MOSFET, and we also have what we call as the N-channel E MOSFET. So this is CMOS, or complementary metal oxide semiconductor, for the enhancement P channel and N channel. Now, for the introduction here, you will see that the field effect transistors can control the current by the voltage applied to the gate. So if you will look at the figure here, it's like the reservoir of water here, which is having a closed gate. And because of this, the source, which is the water from this reservoir, will not be flowing through our channel and going to the drain. It will not happen. Now, on the right side, we see an external energy represented by a person here, which in real circuit will be the voltage that will be controlling the gate. And because of that, the strength of the flow of current will depend on the external energy here, which is the voltage. Therefore, the current, or represented here as water, is being controlled by the gate, which is being controlled by the voltage or an external energy. So the amount of water that will flow from the source to the drain will depend upon the gate, and the gate depends on the voltage or the external energy here. So what are the similarities between the FET and BJT? Both of them can be used as an amplifier, as a switching device, or can be used in impedance matching circuits. How about the differences? The FET control the current by using a voltage source. So FETs are what we call as voltage controlled devices, while the BJTs are called current controlled devices. The FETs have a higher input impedance, and compared with BJT, they have higher gains. FETs are less sensitive to temperature variations and are more easily integrated on ICs. FETs are generally more static sensitive than BJTs. So here is a representation of a bipolar junction transistor. This is the NPN BJT, and as mentioned before, it is current-based. And the I base, or the IB, will be the one that will control the IC, or the current between the collector and the emitter. This, by the way, is the structure of the NPN BJT, while this one is the BJT symbol. Now, on the right side, you will see that the junction field effect transistor is voltage-based, and you will see it here that there's a voltage source here, VGG, and take note that this is negative at the top and positive at the bottom, which is connected to the gate. And then in the structure of the JFET, you will see there's an N channel here represented by the letter N, and there's P-type on the left and on the right. And this is how to connect our JFET in a circuit. Now, the voltage gate or the voltage coming from the VGG will control the current that will be flowing from the source to the drain. By the way, this is the structure of the JFET. You will see the D for the drain, G, which means a gate, and S, which means source. And take note, this is negative VGG here, and the VDD on the right, positive at the top, negative at the bottom. This is an example of the connection of an N-channel JFET, and this is the symbol for the JFET, which is N-channel. Next, what do you need to know about the symbols and short forms? So VGS stands for gate to source voltage. VDS stands for drain to source voltage. VGG means the voltage supply at the gate terminal. VDD is the voltage supply at the drain terminal. VP is the pinch off voltage. ID is the drain current. IDSS is the drain to source saturation current. When we say N-channel, this refers to the N-type material. And P-channel refers to P-type material. So the resistance of the field effect transistor when VGS is equal to 0 can be written as RD. And the resistance of the FET when we have a particular level of voltage in the VGS is called RO. Now, the JFET primary characteristic, the JFET transistor controls the current flow, of course, and the JFET uses the voltage to control this current flow. And if you will remember, the BJT transistor uses the current flow through the base emitter junction to control the current, or it uses the IB to control the IC. That's for BJT. But for JFET, it uses the voltage to control the current. JFETs can be used as amplifier, just like the BJT. And the VGG here is the voltage level control. It controls current flow in the VDD RD circuit. So the current that flows in the VDD in the RD circuit is controlled by the VGG. So again, this is the structure of the N-channel JFET, and this is the structure of the P-channel JFET. You will see that there's a P-channel in the middle. Just put letter N here. I think this is a mistake. There should be N on the left and N on the right here. So this is the drawing for the structure of the P-channel and N-channel JFET. And this is the symbol for N-channel JFET. Drain at the top, gate in the middle here, and with an arrow, and then the source. Drain, gate, and source. But the arrowhead, when it is going in, is the N-channel, and when it is coming out, that's the P-channel JFET. Now let's look at this representation of the JFET again. So the source drain current here between the source and the drain is controlled by the voltage field at the gate. So these fields, or what we call as depletion layer, is developed by the reverse bias gate source here. But let's say that there's no gate source voltage here. Of course, there will be, you will see here that the DC voltage source here is not connected, and we will increase this, or we will put another voltage here aside from 0 later on to see the effect on the right. Let's say we put a voltage here more than 0 or not 0. So this will have a depletion layer here. And the more voltage you apply in the reverse bias here, the more the depletion layer, the field will grow or becomes larger. So this field, or we can represent it, or we can say like a resistance, will limit the flow of current between the source and the drain. So as you can see, compared before, let's go back. There's a wider channel for the current to flow, but the moment you apply more voltage source on the gate, then the depletion layer will be bigger, or in effect, the channel will be less in size, or will be narrower, and the current can. It's possible that if you still continue to increase your voltage in the gate, then no current can flow in the channel. So when you have no current or no voltage, I mean no voltage here or zero, we have no VGG, the current will be at its maximum. But when you put a maximum voltage here, the current will be at the minimum. So it's similar to saying that the higher the resistance, the lower the current. In this case, the higher the voltage on the gate, the lower the current will be. And this is because of this layer or depletion layer that is developing on the P-type material here in the middle. So if you will look here, we have here 0 volts in the gate, and there will be a huge amount of current that will flow here when the voltage on the gate is 0. But the moment you increase this voltage, then the current that will flow on the channel will be smaller until such time that no more current can flow. That is when the voltage in the gate is 0. Here you will see the JFET, which is biased for conduction. And as you can see here, the voltage VGS that we measured on the gate is it's like 50% of the voltage source. So the negative voltage source here is like around 50%, and the current that we are producing on the ID is also 50% of the current value. Now, the moment you increase the VGS here, the greater VGG will narrow down or make the channel narrower between these white areas that you see here in letter B, and this will be like increasing the resistance of the channel, and in effect the current here you will see is much lower compared with the original half value that we see here. So you can see it's like close to 1/4 current now when we increased the VGS from 50% maybe to around 75%. Now in letter C, we will see that the ID is much higher when you put a lower VGS on the VGG. So these are some examples of how the JFET is controlling the current, and that is through the variation or changing the value of the VGG. So again, letter A is for middle bias for moderate current flow. Letter B is for maximum bias, or it's like the current will be very small, or we call this pinch off or almost no current flow. And letter C is what we call as low bias for maximum current flow. Now for the JFET operating characteristics, there are 3 basic operating conditions for a JFET. The first one is that the VGS is equal to 0 volts, so the VDS will be increasing, but this will be increasing, of course, to some positive value. Now, when the VGS is less than 0, the VDS or the voltage DS will be at a particular or at some positive value. And the third case is that we are controlling the voltage, or we say voltage controlled resistor situation for our JFET. So for the JFET characteristics and parameters, we have what we call here as the ohmic. When we say ohmic region, this is from point A to point B. So if you will look at the effects when we increase, when the VGS is 0, so let's say there's no VGS here, or the VGS will be 0, then the ID increase proportionally with increases of VDD. So if you adjust the VDD while keeping the VGS equal to 0, the current ID, when you increase the VDD, will also increase from point A to point B. And while it is increasing, this is what we call as the ohmic region from point A to point B. Now for the pinch off, when this is the point when the current on the drain or ID stop to increase even if you increase the VDD. So the situation is the same. The VGS is equal to 0 because there's no VGG applied. And when you change the VDD and it's no longer affecting the ID, it means you already have started the saturation point of the IDS. So we call this saturation current as IDSS. This is from letter B to letter C in this drawing. And you will notice that the IDSS is constant. And again, this is while the VGS is 0. And while you are varying or changing the VDD, the ID is still the same. So this is what we call as you have reached the IDSS, or the pinch of or constant current area here. Now this current is called maximum drain current or saturation current of the IDS. And this letter C, on the other hand, is the point where we call it as breakdown. And this is only happening when you still increase the voltage or the VDD, you still continuously increase it in such a point where the transistor is broken. So that's what we call as the breakdown region. So we don't like this because it means our JFET will be broken, and the operation of the JFET must be always be below this point, not above, because this is not what we want to happen. So all in all, this picture or drawing or diagram where we have the VDS on the x-axis, ID on the y-axis, and we have here the IDSS, we have here the start of the saturation, which we call as the VP or pinch of voltage. We call this characteristic as the drain characteristic. So again, this drain characteristic was achieved while our VGS is equal to 0. And we vary the voltage on the VDS by controlling the VDD. Now to continue, this is the drain curves or set of drain characteristic curves. And from this set of curves, you can see that the negative voltage applied to the gate. So starting from 0 volt, we increase it to negative 1, negative 2 volts, negative 3 volts, negative 4 volts, up to negative 5 volts. Now, let's say this is the VGS. The VGS is negative 1 here. So when the VGS is negative 1 here at this point, represented by this pink curve, here we will put VGS equals to minus 1 volt. And this point here is the pinch off when the VGS is negative 1. When your VGS is equal to 0, this point here is the pinch off when the VGS is equal to 0. Now, you will notice that when the VP is equal to positive 5 volts, the VGS off, as we call it, is equal to negative 5. So if you want to get the VGS off and you know the VP, just take the value of the VP but make it negative. And if you know the VGS off is minus 5 volts, then the VP is also 5 but opposite. It's not negative, it will be positive. So this is an example of the family of drain characteristic curves. And this pink drawing here or curve represents the VGG when it is when the VGS when it is negative 1 volt. So this is negative here. So the voltage source here is negative 1 and the VGS will be, of course, negative 1. Now the ID, from this set of curves, you can see that I have said the increasing the negative voltage applied to the gate produces no change in the ID. And when there's no more change here, like here, we have reached the saturation point. So from the negative VGS, so from negative 5 volts, then the ID will no longer change. And the ID is limited and the pinch of voltage is, of course, reduced here. You will see that what I have said to you is that VGS of -5, the BP will be positive 5. Now we know that as the VGS is increased, the ID will also increase, and the point that ID stop to increase is called the cutoff. So the saturation point that I talked about, we call it as the point where the ID stop to increase, we call it as the cutoff. And the amount of VGS needed to do that is what we call as the cutoff voltage VP. And the field in white here grows such that it allows no current to flow in our channel. Now, it is interesting to see that the pinch of voltage VP or VGS off and cut-off voltage are the same, but they have opposite polarity. As I have said, if VP is positive 5, the VGS is negative 5. If the VGS is negative 5 volts, therefore the VP is positive 5 volts. So the VGS and VP are always equal but opposite in sign. So if the VGS is negative 5, the VP is positive 5 volts. The VP or the pinch of voltage is the value of the VDS where the ID becomes constant with VGS equal to 0. The voltage pinch off also occurs for VP, which is more than VDS, if the VGS is not equal to 0. I think I have shown you this diagram in the previous page. Note, although VP is constant, the VDS minimum where ID is constant will vary. So again, this is the VGS of -5 volts, and this is the VP, positive 5 volts. And all of these are called family of drain characteristic curves. Now, for the JFET characteristics and parameters, the transfer characteristic curve illustrates the control VGS has on ID from cutoff or the VGS off to pinch off. Note the parabolic shape here that you will see represented by the light blue color here, and the formula that we can use to determine the drain current is IDSS multiplied to 1 minus VGS divided by VGS off to the power of 2. So IDSS multiplied by 1 minus VGS over VGS off close bracket to the power of 2. Take note that the VGS is equal to 0 to VGS off to control the ID. So this is from 0 here, increasing it up to a certain value to control the current. And then you will reach the IDSS. So all of these curves has its own IDSS. Here it's 12, here it's 7.68, here it's 4.32, and so on. So if you continue to increase negatively the VGG, the VGS will be increasing to -4, and the current ID will be closer and closer to 0. And again, if your VGS here is -4, it means that your VP will be equal to positive 4. We will see that when we do the calculations later on. So this is the VP and this is the VGS of negative 5. The VP is positive 5. Now the square law device, this is like a parabolic curve of the JFET characteristic curve. Now this is about the transfer conductance or forward transfer conductance represented by GM of JFET is generally considered as forward transconductance. It is the nonlinear changes in ID based on the changes in VGS. So the formula for this forward transfer conductance is delta ID over delta VGS. And this is parallel concept of voltage gain. So this is our curve. You just put a point here on the curve and another point. It means you need to put 2 points, and this point, let's call it GM2, and this point, let's call it GM1. So the GM2 will be equal to delta ID2 divided by the VGS, and this is what we call as GM2. So ID over VGS. And GM2, of course, must be greater than the GM1. Now, the delta ID2, it means you will subtract ID2, the ID here and the ID here, that's called delta ID2. So if you have here 7 and you have here 3, 7 minus 3. So the delta ID1, on the other hand, the point from here minus the current ID here, the difference divided by the VGS will be our forward transfer conductance. So this is the another characteristic, or we call it just the forward transfer conductance. So the input resistance for a JFET is high since the gate source junction is reverse biased. And this is the formula that I can show you. Rin is equal to VGS over IGSS. The IGSS is the gate reverse current at a certain gate to source voltage. So the IGSS here is the current at a certain VGS. However, the capacitive effects can offset this advantage, particularly at high frequency. Remember, for those who knows about varactors. Now, the drain to source resistance is the ratio of changes of VDS to ID, and the large changes in VDS produce very small changes in ID. So this is the drain to source resistance represented by R prime with a subscript of DS. So again, in JFET biasing, just as we learned that the bipolar junction transistor must be biased for proper operation, the JFET must also be biased for operation. And we can take a look at some of the methods for biasing the JFET. And in most cases, the ideal Q point will be, of course, the middle of the transfer characteristic curve, which is about half of the IDSS. Now, when we say self-bias, this is the most common type of biasing method for JFET, and no voltage is applied in the gate, and the voltage to ground from here will be 0. However, the voltage VGS or the gate to source voltage will be negative for the N channel and positive for the P channel, keeping the junction reverse biased. The voltage can be determined by the formulas below. So ID is equal to IS for all JFET circuits. For N channel, the VGS, as you can see here, will be VG minus VS, and VG is 0, so 0 minus IDR. So that will be equal to negative IDRS. And for P channel, the VGS will be equal to VG minus the negative of VS. So the P channel, the VGS is equal to VG minus the negative of VS, or 0 volt minus minus, which will become plus. So positive. So 0 minus minus 0 will be 0, and minus minus will become plus. So it will be plus ID or plus IR.